we ended yesterday, which is at point and non-point solution, pollution. Did I say that right? Okay. So anyway, we had done this a little bit yesterday, and I think at the end I kind of rushed through it a little bit. And the mines was like the last thing as the bell rang. And I said that if you have just one pile of mine tailings, which is like the leftover stuff after you remove the ore, if it's just one pile you can point to, that's point source. But if you have a large mining compound and you have many, many acres, then that's non-point. So I'm not going to tell you what that is. Water pollution can have many forms. We had talked about these, and we had spent a lot of time on them when we did the lab with water quality testing. Your book doesn't go into those different chemical tests as much as we did, but the AP exam does, and you'll find that you'll need to know those for the free response. So you can refer back to your notes in that case. Anyway, so fecal coliform, that test was kind of important. Basically, what we had done there is I had that little vial, and it had turned yellow, which indicated that there was fecal coliform present in both water bodies. And when you have fecal coliform present, that's not like the worst thing that you could consume, but it's just an easy bacteria to culture. But it tells you that poop's in the water, and so worse things that could happen to you, like typhoid or hepatitis, or a big one is cholera. I wish your book had mentioned cholera. That's really the biggest one as far as waterborne diseases. So if you have fecal coliform in your water, it's possible that you also have hepatitis A and cholera. And so in developing countries, these kind of things, these simple water pathogens are very abundant because they don't have water treatment, and they can cause death because if they do get sick, they don't have clean drinking water to help rehydrate them. Anyway, treating drinking water is helpful. Nutrient pollution, the biggest thing for nutrient pollution, if you recall, we had talked about if we have a lot of nutrient pollution, you're going to have a high biological oxygen demand. And that's where I drew those 2 bottles of water or beakers of water, and I had put little white dots and the brown dots. And I had explained how if you have respiration breaking down your organic material, it's also going to use up dissolved oxygen. We tested that on the first day and on the third day. Do I need to draw that again? Do you remember what I'm talking about? You okay with the biological oxygen? It's just a measurement of who condensed up in the water. Okay, so fecal material, if you want. Try to make this as easy as possible. All right, so if we do have a high biological oxygen demand, that means that the oxygen demand is going to be high, and so I'm going to end up having low dissolved oxygen. And so after that nutrient pollution occurs, we can have areas of low concentration called dead zones. They're also called hypoxic zones. And they're also called areas of oxygen sag. And the reason I bring up oxygen sag, when the people run the AP exam, they look at the most popular textbooks, and one of the more popular textbooks uses the term oxygen sag instead of dead zone. And so, I mean, just in case you see that, there you go. Anyway, if you look right here, phosphate containing detergents, that was banned. It's now legal. But for a while, like I told you, it made your whites brighter than white, and they did that on purpose. They made your clothes kind of glow to be brighter, whatever. Obviously, fertilizer is an issue. And then, if we're going to plant vegetation to reduce the runoff of nutrients, we're going to plant the vegetation, guess where? In the riparian zone. So if you have a large cornfield and it backs up to a river, if you take and you plant corn along the edge of your property where it meets the river, what is going to happen is those trees and those bushes or whatever, those are going to take up the nutrients like nitrogen and phosphorus before they get into the river. And so that will help if you increase, it's kind of like a buffer zone of vegetation between your farm and the water. So that's helpful. Anyway, so there's where that word will come back over and over again, and you'll see it a lot. And that's another way that you'll see it. So we had talked about oligotrophic and eutrophic water, and I had sort of described what it looks like, but that's what it looks like. Have you ever seen anything like that top picture around here? No, that's not a thing. Like Lake Baikal, the largest and the most water-containing lake in the world, deepest freshwater lake. What?
Where is it?
It's in Siberia. And so the thing about oligotrophic lakes is they have really high dissolved oxygen. And places that have really high dissolved oxygen are going to be in colder climates. So most of these illegal trophic lakes are in Canada, Russia, and then sometimes in mountainous areas like Colorado where you have good amount of elevation, so you have colder temperatures. But most of the lakes in Canada, did you ever go to any lakes in Canada? Do they look like the top picture or the bottom picture? The bottom picture. They're eutrophic?
No, they don't have that much, but like
They're cloudy.
they just look. Yeah, you can't see them. You can see about 5 feet down.
Okay. Well, and something else that goes into play, especially in Canada, if you're probably going to a lake, it's probably the spring or summer, you have a lot of the glacier melt, a lot of the snow melt, and that's going to carry sediment and make the water more turbid. So that's possible too. But in areas like Siberia where it just never really thaws out, you got that. But this is what we're more used to, the eutrophic water. So there's that. So thermal pollution. Thermal pollution can go two ways. It can be hot water or it can be cold water. It's not just hot water, but most commonly thermal pollution will come from factory output. So we're going to use water to cool our power plant. We're going to use water to cool our factory. And so what ends up happening, dissolved oxygen is going to decrease as temperature increases. So the hotter that water gets, the less oxygen it can hold. The water molecules are moving around more quickly, and the oxygen is going to get knocked out of solution. I think tomorrow while I'm lecturing, I actually have some cans of carbonated water. They're not Coke, they're just carbonated water. I've used them in chemistry. And I'm just going to take a can, and I'm going to test the pH. And then I'm going to just repeat it throughout the class, and we'll test the pH periodically. And the pH, if you think about it, should go up because of carbon dioxide, which makes carbonic acid, will come out of solution as the water heats up. That's my prediction. I don't know. I've never done it before. How's that sound? Kind of fun? We can go get one right now. Want to go get one? I kind of want to. Yeah. Okay. The pH paper, though, none of my lab mates are in here. Olivia. So somewhere, you know that vac hood where I blow stuff up? I think laying on that is some pH paper. And then there's a can of carbonated water in the refrigerator. So good luck. And force you with you. Anyway, so water that's too cold also can cause problems. And generally what happens when you have water that's too cold, what's happening with that, and I had talked about this a little bit yesterday, water that's too cold comes from a dam. In the reservoir behind the dam, you're going to take that water and you're going to take water from the bottom of the reservoir, which is going to be really cold, and you're going to use that water, you're going to pull it to the dam to turn the turbines, and then what's going to end up happening is it's going to run into that stream, and that stream is going to have much colder water than it would normally. And so that really rapid decreased temperature of the water is going to, it could be at a temperature that's out of the range of tolerance for the fish, and so it could cause them to die. So anyway, I'm going to pause this so I can get the hot plate. Plus Olivia didn't hear all that. Alright, so chapter 15 was about freshwater. This one's about ocean water, marine water. The case study for this chapter was the fishing grounds in the North Atlantic. So here, guys, these guys are catching, looks to be probably cod. And so these are ground fish, Grand Banks and Georges Bank. These places were really lucrative, awesome fishing grounds, and they changed history and all this stuff. No fish has ever had more impact on civilization than the Atlantic cod. Fish for generations, centuries. Any kind of benthic fish, ground fish, halibut, flounder. Flounder are the ones that have that two eyes on the same side of their head because they bury under the ground like the sediment. Do you know which one I'm talking about? And they're like, yeah, and so they don't need like an eye on the other side because well, they're going to look at the sediment. Okay. So anyway, they live in the cool waters on both sides of the Atlantic. So like people in Scandinavia, they also really like cod and they use it. They like salt it, like Swedish people salt it and put it in a jar and all this stuff. Yeah, it's gross. But anyway, I actually was watching a commercial not too long ago, and then they were talking, it was like Wendy's, and Wendy's was like advertising this Pacific cod sandwich. Did you see that? Yeah, the Atlantic cod, they're totally overfished, and so now that's what we do. We overfish a fishery, and then we go exploit it differently. And so they're starting to exploit the Pacific cod. So, which is kind of scary considering. But most, especially in the developed world like us, we have, like with crab fishing and North Pacific fishing, most of those are regulated and have fishing seasons and things. They actually closed this fishing area in 1994. In 2011, so, you know, you're looking at 17 years later, they're starting to rebound, but that's still not open to people having a boat and doing this for a living. You can see all the areas that were close to fishing, and that's because they were completely overfished. What ended up happening here, I'll go back a little bit. What ended up happening was they caught all the large desirable fish, and so then the baby fish are typically prey for larger other species of fish. And so you didn't have any large, vigorous individuals left to populate. All the smaller ones were all that was left because we wanted the big ones because we make money off of them. And they harvested below half of the carrying capacity. All right, so there's that. Oh, oceans. So we had talked about 71% of the land, the surface on Earth is covered in water, and then 30% is covered in land. Other facts we had talked about, 40% of the land on Earth is agriculture, 30% is forest. But of the whole Earth, not the dry part, the whole Earth altogether, the whole Earth altogether, 71% is covered in ocean. And they're one vast body. So there's that. This picture is really good. It kind of goes over so many things that we talked about already. So let's go out into the parking lot of our minds. And this right here, this is the concrete. So this is my continental crust, right? And this shelf here is the sidewalk. It's elevated up, okay? And then we had talked about the asphalt where the buses park. That down here, this is the abyssal plain. This is oceanic crust, okay? And then there's a break here, and it drops off, literally drops off, because the continental crust is so much thicker than the oceanic crust. If we look here and we add in some geology, because geology's fun, here I have a magma coming up to the surface, and this is actually a divergent plate boundary. This is where I'm making new crust. And if you look, this is a subduction zone. This crust is going down, it's getting melted, it's coming up. This is volcanoes. Sorry. Well, this is how Japan's made. I mean, I know it would be on the other side of the ocean, but this is a subduction zone. It's a convergent plate boundary. It has a trench. This is a volcanic island arc. Are these ringing some bells in your mind? Hopefully. But the Georges Bank and the Grand Banks, those are on the continental shelf because also the crab fishing in Alaska. Have you seen some of the shows where they have cages and they throw them out and they go to the bottom and then the crabs are walking along the bottom of the ocean? That's done on the continental shelf. I mean, those lines that they throw out, are they like 2 miles long? No. So there's nothing down here in the abyssal plain. Okay, so it's up here on the shelf. Yes, ma'am.
So is the continental crust, crust where it drops off into the abyssal plain? Is that like in Finding Nemo drop off?
Yes. That could be a trench. I don't know. I mean, it's a cartoon. But there's parts of the continental crust that extend out to the ocean, but they're just under the water. But there is definitely a drop off, and that probably. Sure, why not? Anyway, this is at the edge of every continent. And so if we add in a little bit more, remember I had talked about chemosynthesis. And so this is my mid-ocean ridge. Mid-ocean ridge. These are my little mountains that go around the whole Earth, remember? And this is where chemosynthesis happens. Oh, it's right there. Sorry. This is where chemosynthesis happens. And the magma coming up is what provides the hydrogen sulfide gas. This magma coming up has a hydrogen sulfide gas in it, and that's what fuels chemosynthesis. Yes, ma'am.
How far out does the shelf go?
So it depends on the area. It's usually, I mean, it could be just a couple miles. It could be 100, more than 100. So like for example with Alaska, if you look at like the Aleutian Islands and then over here is Siberia, that looks awful. And I don't have this like memorized, but like if that's the Aleutian Islands and that's Alaska, that looks good. And then over here is Siberia, and then you have that crazy little thing, and then Japan's, you know, way over here. This whole area up in here is continental shelf, and it's very shallow, so it's good fishing. So anyway, it depends, but it's at least a few miles. It could be a lot. So there's a nice review of geology and the bottom of the ocean. So the shelves, that's where we fish. And this is the shallow part. It's still continental crust. That's all there is to that. The AP exam doesn't really have a whole lot of bathymetry, which is, you know, figuring out how deep it is and stuff. If we look at salt water itself, salt water, if I take a sample of ocean water, it is 96.5% water, and the other 3.5% is the salt. Okay, so if I put one of those little things, remember how I made the light bulb come on? If I put that in ocean water, then the light bulb will come on a lot faster, or a lot brighter, I should say. Sorry, a lot brighter, and then tap water, and then of course, you know, pure water doesn't have that ability to conduct electricity. Alrighty. So yeah. Here's the salts. The most abundant salts in the ocean are sodium and chlorine. Is that surprising to you that the salt water in the ocean, the most abundant salt is sodium chlorine? So sodium chloride. You know, when we think about salts, when we think about ionic compounds, people just think of sodium chloride, but any two, like a metal and a non-metal bonded together, that's a salt, and it makes a white thing in it too. That's a salt. It doesn't have to be salt to be a salt. Anyway, can you think of any positive biological processes that need a lot of sodium? Doesn't that like if you have blood pressure and like a heart attack? Right. So there's a reason why sodium and chlorine are the most two abundant ions in the ocean. Those are the things that get taken up by life and pee right back out because they're not needed. You sweat salt. It's in your urine. It's in your tears because your body doesn't need it. Okay. And so all the little animals on Earth are taking out these minerals and rocks and stuff. They're eating stuff. They're doing stuff. And they're peeing stuff back out, and nobody keeps that in their body. But stuff like calcium, things like potassium, and bicarbonate, and these things, magnesium, that stuff's in vitamins. Like, you need that, right? Yeah? So, seashells, remember seashells? Seashells are made out of calcium and carbonate. So there's not a whole lot of that in the ocean because all the little clams are picking that up and making a shell out of it. Coral. Crap, well, they make chitin, but anyway, so any kind of seashell and coral, they use calcium carbonate. So that's a limiting factor for growth in the aquatic ecosystem, along with nitrogen, phosphorus, and potassium. Anyway, the water, if I look at water in the ocean, let me just kind of draw this out for you a little bit. If I have at the surface of the ocean, I'm going to have warm water. I guess okay, whatever. Can we all agree on that? Does that make sense that the top of the ocean is warm? And just crazy talk. I'm going to have cold water at the bottom. And the reason for that is because cold water is... What?
You just didn't look at it.
Whatevs. So cold water is going to sink because it's more dense. And hot air rises because it's less dense and it cools it against the big clouds. You've heard that sentence before, I know you have. So just like that, water does the same thing. How do you feel about it? Is that okay? So also, if I take salty water, do you think it's probably more dense or less dense than pure water? Probably more dense, right? Because it has stuff dissolved in it. Does that make sense? So the deep water in the ocean is very salty. And the water at the surface is fresh. And another reason the water at the surface is fresher, it's not totally fresh, I mean it's in the ocean. But the reason it's fresher is because it rains at the surface of the ocean. It doesn't rain in the water. Now, so this is less dense, and this is more dense. And this seems really easy, like why are you telling this? And then there's a very fast transition. And it's called the pycnocline. I feel like I'm going to spell it wrong.
Pycnocline.
Got it now. So this is called the pycnocline. This is the area where the density increases rapidly. So at the surface, you have surface water, everything's cool. You have deep water, everything's cool. And they don't mix. There's a very clear transition zone that's sharp, very fast transition. And it's called the pycnocline. The thing is, this deep water, cold, same temperature, same salinity. It does not matter if you're at the equator or the North Pole. That deep water is cold and salty. It has about the same temperature and the same salinity. That surface water is going to vary with what latitude you're at. Obviously, it's going to be warmer and colder. But that deep water is deep and cold and salty everywhere.
So even like in near the equator or at
Once you go below the peak decline, it's all the same. Very, very similar.
is that like miles deep?
Yes. So, I mean, the average depth of the ocean, I won't say anything wrong. I know the deepest place in the ocean is 5 miles deep. Your average depth, 1 to 2 miles, something like that.
It's so weird because you think like, okay, you get closer to the core where it's like super, super hot, you warm it up kind of make it move.
Well, the core does transfer heat to the surface, but it does so only at hot spots and lake boundaries.
Well, I mean, just when the water's like 5 miles deep, and it's closer. I don't know. That's just so bizarre. The world.
But the surface of the Earth isn't. I see what you're saying, but I gotcha. Yes, ma'am.
Could you like feel the picking up line or whatever on like Google Images?
Oh yeah, and with El Nino, which we're going to talk about tomorrow, I'll show you the pink decline in my little aquarium. But that's a totally thing, yeah. And so you can actually see the warm water moving around, and then below the pink decline, nothing happens. It just stays. Huh? Yeah, that one. I'm going to show you El Nino tomorrow. I got it on my list of things sitting. So anyway, there's that. Oh, here's all the stuff I just talked to you about. There's the surface. It's warmed by the sun and stirred by the wind. Because it's stirred by the wind, it has high dissolved oxygen. All of this stuff. We just wrote all this down. And like I said, that pink decline is this sharply changing area of density. All right. So the deep zone is the zone below the pink decline. It's dense, sluggish water. It's not affected by winds. It's not affected by temperature. It doesn't matter. It doesn't matter. It doesn't matter. It doesn't matter where you are. It's all the same. So anyway, and I know I've told you this. Water has a high specific heat capacity, so it's really hard to heat and cool. Have you heard that sentence come out of my mouth before? It sound like something I said? I feel like I've said that before. So it takes more energy to heat and cool it, and so it's going to help to moderate and regulate our climate. If you live near the ocean, the temperatures aren't going to change as much as they do near land. Yay! And so if I look at a picture, let me make this go away. I don't even know what that is. Whatever. Go away. If I look at a picture of the ocean, you guys did a pretty good job when you talked about this in your presentations. You can see that the ocean currents actually kind of move around in like a circular, right here. When I was in college taking all these earth science classes, I mean, we have to draw these. I have them on memorized and can tell you like a ton about them. But the thing about the ocean currents, if you look down here near the Antarctic where there's no land, they flow in a straight line all the way around the Earth. And those winds down here are super fast. But if we look everywhere else, the winds are trying to go in one direction. Look right here. All these winds right here are trying to go that way. Do you see it? Yeah. And all these winds right about here are trying to go this way. And so the thing is, they can't keep going straight because that whole like land thing's in the way. And so they're trying to go this way, and they get turned and they come back. And so they make these circles called gyres. And those gyres are where you get those garbage patches. And the garbage patches are in every gyre, not just the Pacific one. The Pacific one is just the worst one. There's a gyre here, and here, the South Pacific, nobody lives there, whatever. But Australia, like 4 people live in Australia. But so those gyres, they kind of move around in a circle like a toilet flushing, and they pull all the trash to the center of it. So that's fun. Whee! So currents, that's what I just showed you with those little black arrows. They're these rivers of water that move the water around. Some currents are really strong, like the Gulf Stream. They're going to transport heat, nutrients. They're going to help marine species move. So like in Finding Nemo, the North Australian current or something, the NAC. Yeah. So they were riding it. That's what they were doing, and a lot of turtles do that.
It doesn't really look like that. Like,
oh no, it really doesn't look like that. It doesn't go that fast. No, but it does. It moves like Christopher Columbus on a ship, but about that fast. That's how they got here. What?
like scurvy.
Yeah. Anyway, so yeah, it's slow enough for you to get scurvy. So the Pacific Ocean. If you look back at those currents, let me show you again. Well, after the tsunami happened in Japan, there's Japan. Oh, this is what I was saying. All of this ocean right here is very shallow. So that's where the crabs are at. Crabs. And you can tell. I mean, you can tell that's ain't like super deep water right here. I mean, the land wasn't gonna drop off 5 balls and then come back.
Well, didn't they say that used to touch, and that's how they think like Native
No.
Americans?
What it didn't touch like what you're thinking. I got you. I'm gonna tell you all the things right now. So if this is glaciers, and this is glaciers, this was glaciers, and then like it wasn't wasn't touching. It was an ice bridge, and then the people walked over here. Whee! That looks good. Anything else y'all want to explain? Anybody want to know where like babies come from, or like? I don't want to explain that. Well, where do rainbows come from? What's sky blue? I got to answer all that, but just not right now. Anyway, people, look. Then we brought the malaria. No, was it what?
Smallpox.
That's it. I don't know. I always have to talk about malaria here when we get to climate change. It's a big thing. Like malaria and cholera, those are the two you have to know for me. But I know malaria is carried by mosquitoes. Don't judge me, okay? I'm sorry. Anyway, so in some special places, when the currents actually come up to the surface, this is not normal. Most of the currents are on the surface, but some places along coastlines where the wind gets, the wind's going to blow the water out of the way, you're going to have deep water coming back up to the surface, and that's called upwelling. And upwelling is going to bring these nutrients. Was it your class that talked about the ocean snow, all the stuff floating to the bottom or sinking to the bottom? Yeah, and so, oh, thank you. So all these nutrients at the bottom of the ocean from all the decaying and poop stuff, it's going to come back to the surface, and that's called upwelling. And this is really important for bringing nutrients to the surface, and it usually makes for really awesome fishing grounds. Yay. I'm actually going to try to show you this in my aquarium tomorrow. If I get the right kind of salad dressing and cross my fingers. And I close my fingers. Yep.
Can you show us the video of the house and how like half of it went?
I got a list of things to do tomorrow. I'm putting it on there. Gotta put your computers up right now. Okay, while you're putting your computers up, I'll find the house that fell in. Tomorrow's lecture goes really fast because you already taught all that stuff, and I'll just go back and reiterate things. So it's like brother, sinkhole. Look, see? I told you, like, it's a thing.
Allowed cracks for nothing.
Yep. I got you. I'm gonna make the green thing go away. Oh, yeah, there it is.